to come up with it being continuous from -2 to 2. So any questions on given a function? Like I said, if they just ask you about where it's continuous, it's basically you're finding the domain. All right, they're not asking for the location, they're not asking for the type of discontinuity. All right, now they're giving you a graph. Like I said, always different ways you have to look at these representations for continuity. Not only algebraic by looking at the graph. So now, two ways they can answer you this question. At which points is the graph discontinuous? So let's start. Give me an x value where it's discontinuous. -2. So I agree with that. And even though it's not asking you, I want you to tell me what type of discontinuity is happening at -2. Is it removable, non-removable, jump, or infinite? Infinite. So we know it's infinite discontinuity. Is there another place where it's discontinuous? 0. And what type of discontinuity is happening at x equals 0? It's a jump, or we can say it's non-removable discontinuity. Where's another place where it's discontinuous? 2. And again, at x equals 2, we have what kind of discontinuity? It's going to be at x equals 2, it will be removable. Because remember, what makes removable is the limit from the left the same as the limit from the right here. Yes. What makes it removable is the defined value is different from the limit from the left and from the right. All right, so any questions from the graph being able to identify where it's discontinuous? So now they're asking me what interval is the graph is continuous. So again, always read the graph left to right. So start at -5. It's continuous from -5 to what? -5 to -2, and I'm going to use a parenthesis at -2. And then it's going to be continuous where? From -2 to what? 0. And then it's going to be what? Continuous from 0 to 2. And then it's going to be what? Continuous from 2 to 5. So any questions on how you can read the graph and find the location of discontinuity as well as the intervals? Yes, Nicole. And why is it removable? The definition of removable, remember what's happened, the limit from the left has to be the same as the limit from the right. So it's non-removable because the limit from the left is not equal to the limit from the right at 0. Versus what's happening at 2, the limit from the left is the same as the limit from the right. Think of a jump this way. You draw a graph, your pencil here. You got to then pick your pencil back up, and you've got to put your pencil somewhere else and continue sketching the graph. Whereas removable, notice if I take my pen, I can sketch the whole entire graph without lifting up my pencil, but I've got to pass through that one point, which is the whole. If that makes it any clearer for you in terms of what's the removable versus non-removable. Okay? Charles, your question?
So, like B, it's not the same as the A.
Right. Right, exactly. Because you have these, because -2 is in the domain, and then 2 is in the domain. The domain in this case would be different than the continuity intervals. Okay? So any other questions? So here's another piecewise function. Find a value k of the constant, if possible, that will make the function continuous everywhere. Well, we know 6 minus x squared is a polynomial function. The domain is all real numbers, correct? X plus k is a linear function. Domain is all real numbers. So if discontinuity were to occur, at what x value would discontinuity occur? It would occur where? At 1. So to ensure, remember what has to happen, the limit as x approaches 1 of f of x has to be equal to f of 1 to be continuous at 1. So to ensure that what's happening on the left and the right are the same, what I'm going to do is I need to set 6 minus x squared and x plus k equal to one another. Remember, I'm solving for k. Because I want what's happening on the left to be the same what's happening on the right. Now, at what x value do I want to assure continuity? At what x value do I want to make sure this is continuous? At x equals what? 1. So I'm going to plug 1 into this equation for x. So 6 minus 1 squared equals 1 plus k. And then solve for k. So 6 minus 1 equals 1 plus k. 5 equals 1 plus k. So what's k going to be equal to? 4. Classic AP question. Any questions on that? All right, last thing and then we're done. Intermediate value theorem. If a function is continuous on an interval, and if k is a number between f of a and f of b, then there is at least one number x between a and b such that f of x is equal to k. So let me put in words what they're or let me put a picture of what they're saying. So they tell you we're continuous for an interval from A to B. So there has to be a continuous from A to B. And K is some y value that's occurring between f of A and f of B. Then what they're saying is there has to exist an x value such that f of x is equal to k. So for example, in real life, suppose that you all were born and you were born, let's say, 21 inches tall. And right now you are, let's say, 6 feet tall. Was there a point in your life where you were 5 feet tall? Yeah, you had to be. You had to continue. That's an example of your value theorem. Even though you were at one point 21 inches when you were born, and now you were 6 feet. There was a time in your life, at some age, where you were 5 feet tall. Everybody agree with that? All right. So now let's suppose that there is a football game going on. We know that the score starts at 0. At halftime, let's say there are 20 points. Was there a time in the game where the score exactly had to be 10 points? No. Because you know you have the 1 point, you have what? What do you have? You have 3 points for field goal, 6 points for what? Kicking. You have variations. There's very different variations in the score. So it's possible that the team had, let's say, 7 points and then scored another touchdown, and it went to, let's say, 13 points, and then they got the field goal. So it didn't necessarily have to have exactly 10 points at one moment in the game. It could skip from 7 points to 14 points. Yes, Lauren? Yes, but we know there's at least one. There's at least one, yes. So when you're stating the intermediate value theorem, you have to state two clear things. You will always state a hypothesis. You always have to state a hypothesis. You must have to state, when you're applying the intermediate value theorem, that f of x is continuous over the interval that's given. And the conclusion is going to have to be that f of a is less than k, and f of b is greater than b, but greater than k. You have to state this inequality. So if you look at this graph, so notice when we talk about f of a, we're referring to the y values. So if you look here on the graph, you agree with me that if this is a k, if this is a y value, f of a is less than this particular y value, correct? Then what has to happen is the y value for f of b has to be greater than k. So as long as those conditions are met, then you can state by the IVT, and it's okay to abbreviate, there exists at least one value where f of x is equal to k. You've got to state the hypothesis. You've got to state the conclusion. And the conclusion is basically you have to set up these two inequalities. One is less, one is greater. And then basically you restate what you're trying to apply to the intermediate value theorem. All right? So let's take a look at, which reminds me I need to go over IUT before their AP exam with my DC kids, because it's been a while since they've done the IUT. So like I said, in the beginning, you must state both the hypothesis and the conclusion when you answer these questions. So if f of x equals x to the third minus x squared plus x, show that there is a number k such that f of k equals 10. We'll need to find our own interval. So first of all, your hypothesis. First of all, sometimes they give you an interval, sometimes you have to state where it's continuous. So first of all, this is a polynomial function. Where is it continuous? All real numbers. So f of x is continuous for all real numbers. Sometimes they give you an interval, sometimes they don't. And this is a case where they don't give you an interval. So this is where if they don't give you an interval, you're just going to set up a t-chart. So what you want to do, again, what we're trying to do is we want to find where, since we want to compare y values to 10, in your table you want to find an interval where your y values, where the y value is less than 10, and where it's greater than 10. So that's what we're looking for. So you can just start plugging in your own x values. Like I said, some of them will give you an interval, some of them won't. This is a case where they're not giving you an interval to check. So again, you can start with 0, you can start with 1. I'm going to go ahead and start with 1. If I plug 1 back into my original equation, 1 minus 1 is 0, 0 plus 1 is 1. Plug in 2. 2 to the third is 8. 8 minus 4 is 4. 4 plus 2 is 6. I plug in 3. 3 to the third is 27. 27 minus 9 is 18. 18 plus 3 is 21. So you agree with me, there's got to be a place between 2 and 3 where your y value is equal to 10. Do you agree with that statement? All right, so now what's my conclusion? Well, f of 2 is less than 10, and f of 3 is greater than 10. So therefore, by the IVT, and again, it's okay instead of writing out, there must exist a k value where f of k is equal to 10 in your interval 2 to 3. That's your intermediate value. That's like your worst case scenario when they don't give you the interval. Okay? Any questions on how you state the hypothesis or the conclusion? Okay? Let's look at another one. Let's suppose that if you have a continuous function, explain why there must be an r value, again they're using r instead of k, for from 1 to r such that h of r is equal to negative 5, and h of 1 is equal to 3, and h of 3 is equal to negative 7. So you can always put a picture to this if you're not sure what's happening. What is h of 1 equal to 3? That is just graphically what? A what? Point. H of 3 equals negative 7 is another point. Again, we've got a continuous function. So are we going to have any holes, jumps, or asymptotes between x equals 1 and x equals 3 if I was to connect these 2 points? No. So here's negative 7. It is impossible, graphically, for this graph to not pass through a particular point where your y value is equal to negative 5. Does everybody agree with that? All right? So now let's prove this by the IVT. So hypothesis. What do I have to state first? I have to state what? That h of r is what? Is continuous in your interval, which they're giving you from 1 to 3. What's my conclusion? Again, it's always that inequality. So f of 1 is what? Greater than or less than negative 5? Greater than negative 5. And f of 3 is what? Greater than or less than negative 5? Less than negative 5. So since f of 1 is greater than negative 5 and f of 3 is less than negative 5 by the IVT. And basically you just restate why there's a value for r such that h of r equals negative 5. So by the IVT there exists an r value where h of r is equal to negative 5. Yes, sure. From 1 to 3. That's not a negative sign, that's just a true. So any questions on that one? Last example. So sometimes you can use to prove you have a solution in a particular interval. So show that f of x equals x to the third plus 2x minus 1 has at least one solution in your interval. They're not specifically asking you to use the IVT, they're asking you to show, which means you can prove it. You are proving it by your IVT. And they're giving you the interval. So they're saying that we have at least one solution between 0 and 1. So all you need to do is find f of 0. And what is f of 0 going to be equal to? F of 0 is what? Negative 1. F of 1 is equal to what? What is f of 1? 1 plus 2 is 3. 3 minus 1 is 2. So now think about what's happening graphically. We know f of 0 is negative 1. F of 1 is 2. First of all, what kind of function is x to the third plus 2x minus 1? This is a polynomial. So is it continuous from 0 to 1? Yes. So I know that graphically it's going to have to be something like this. When I say a solution, what do you know about the y value graphically? If I ask you for a solution, what is the y value going to be? Well, graphically, how do you know where your solutions are? Your solutions are the same as what, graphically? X-intercepts, right? That's where your solutions are. Because on all the other examples, I was giving you a y value of, let's say, negative 5, or I was giving you some other y value. What y value am I comparing this to now? If I'm asking for a solution or an x-intercept, what is the y value at the x-intercepts? 0. So the y value you're looking at is when your y is equal to 0. So first of all, you have to state your hypothesis. So f of x is continuous. And what's the interval they're giving you? 0 to 1. Your conclusion. Again, remember, you're making your comparison to 0. What is f of 0 when compared to 0? Is f of 0 greater than 0, or is f of 0 less than 0? What do we find f of 0 to be? Negative 1. So is that greater than 0 or less than 0? Less than. So I know that f of 0 is less than 0. And what about f of 1? Greater than 0. So since f of 0 is less than 0 and f of 1 is greater than 0, then by your IPT, there exists at least one solution in the interval. 0 to 1. So this is where they actually give you the interval. All you do is you plug in your endpoints. You plug the endpoints of your interval into the function. All right, and then again, here's where they're not specifically giving you the y value, but you have to recognize, well, if it's a solution, it's an x-intercept, which means the y value is equal to 0. Okay? Yes, Molly?
So when I only did switch from discontinuous very happy, but they're just going to stay really quick.
What do you mean?
Like, how all of a sudden they close this group and like this view of procedure, right? That would it ever be like, oh, show this and then it could be wrong?
That's why you always state the hypothesis. The hypothesis is critical because this would not apply if it's not continuous in the interval. That's why you always want to check for continuity in that particular interval.
So you don't employ this.
No. I mean, you may later on, but like for our purposes right now, we're just touching on the very beginning of this IDP. Again, there's really 3 major theorems in calculus that come up, and this is one of them. But it relates to continuity, so that's why we're bringing it up to you now. So when you see it next year, it relates to continuity. Okay? All right, questions on that? All right, and you survived the first chapter of calculus. Congratulations. Seems not so bad, is it?